Dear friends, in session 1 we have discussed about introduction to operations research, in which we have discussed the concept or meaning or definition of operations research, applications of operations research, tools and techniques of operations research. In session 2 we have discussed about linear programming formulation. So in the sense, okay, have formulated a problem as an LPP. In this session we are going to discuss linear programming graphical solution, that is how to find solution of formulated or the given problem. So assume that there are two variables x1 and x2, maybe in the problem of calculators, radios, that farmer problem, all those. So then how to get those decision variables? So we can effectively use the graphical method in obtaining solution of the formulated or given problem. That's what we're going to discuss in this session 3. These are the learning objectives of this session. After watching this video or this session, you should be able to solve an LPP using graphical method, understand the special cases in graphical method, and to understand the limitations of the graphical method. Coming to the steps or procedure of the graphical method, it can be used when there are two decision variables. So this is very important to note here. The limitation or the viability or feasibility of graphical method is it is useful only when there are two decision variables like x1 and x2. If there are more than two variables, the graphical method cannot be used. For that, okay, you have different methods, so known as simplex method, dual simplex method, and its variations or variants, which we are going to discuss in the next sessions. They are called analytical methods. So now coming to the graphical method or procedure, I mean steps or procedure, very first thing that you have to do is, very first step is plot the constraints by converting the constraints means usually the inequalities, into the equations. If some constraint is there, okay, constraint 1, let us say less than or equal, that you have to treat as equation. You have to find the coordinates. Okay, this we'll see in a problem. Fine. Then you have to obtain the coordinates, assuming x1 as 0 once and x2 as 0 once. You will get the pair of coordinates. You have to plot that constraint. So like that, okay, if you have 2 or 3 constraints, you have to plot all of them. That is step 1. Now, satisfying all these constraints, you have to identify common area, that is known as feasible solution space or feasible region. Sometimes identify the feasible solution space or feasible region, that is the common area satisfying all the constraints given in the problem. Now coming to the step 3, obtain the value of the objective function at each corner of the feasible region. Once, okay, if you get the feasible region or feasible solution space, so you will be having the corner points of that. It will be like a triangle shape or any irregular shape, let it be. So but it will be having the corner points at each corner point. So you are supposed to find the value of objective function. So then step 4 is based on the objective, that is based on the z, whether it is min or max. Declare the value of the objective function and the corresponding variables. So if it is minimization, okay, wherever you get minimum, no, so that is the value, and you have to take the corresponding coordinates as x1 and x2. If it is maximization, if it is z max, so wherever you get maximum, I mean at which corner you get the maximum, so that is the answer, and corresponding coordinates, I mean x1 and x2 are the decision variables. Now let us take a problem where you have to formulate and solve. So as I told, in session 2 we confined our discussion only for the formulation. So we have not discussed about how to solve it. So in this problem, so it is given to formulate and solve. So let us understand what is the problem. A computer company manufactures laptops and desktops, which fetches the profit of rupees 700 and 500 per unit each. Okay, so afterwards each unit of laptop takes 4 hours of assembly time and 2 hours of testing time, while each unit of desktop requires 3 hours of assembly time and 1 hour for testing. In a given month, the total number of hours available for assembly is 210 hours and for inspection is 90 hours. So you are supposed to find how many units of each of the two types, that is laptops and desktops, to be produced in such a way that the total profit is maximum to the company. So now, as I told, okay, you please understand the problem very clearly before attempting to solve it. Here you have to analyze, like a case study, how to analyze. First thing is how many variables are there. Okay, you have two variables, laptops and desktops. So step 1 is, okay, we have discussed about steps of formulation. Step 1 is declaration of the variables. Let x1 comma x2 be the number of laptops and desktops to be manufactured. Okay, that is step 1 is clear. Step 2. So it is given that 700 is the profit on 1 unit of laptop, 500 is the profit of desktop, from desktop on 1 unit. So 700 x1 plus 500 x2 will be the total profit from both the laptop and desktop. So hence Z equals to 700 x1 plus 500 x2. So as it is profit, no, so you have to consider this as Z max. So this is about objective function. Objective function is a linear function, of course, and that involves the decision variables that you have declared in the first step. Now coming to step 3, no, constraints. Constraints in the sense you have some conditions. So what are the conditions means? So first thing is requirement of this one. Laptop takes or requires 4 hours of assembly time and 2 hours of testing time. Desktop requires 3 hours of assembly time and 1 hour for testing. So this is the limitation that we have on the availability of what is it called, assembly time and testing time. Okay, they'll assemble and they have to test, no? So that is quality control pass, something like, fine. So in a given month, the total number of hours available for assembly is 210 hours, for inspection is 90 hours. And so each unit, no, consumes so many hours of assembly time and inspection time, all that is given. Now let us divide this problem into two stages, because first you have to formulate, then you have to give the graphical solution also. So you please note that when it is given only to formulate, so no need to solve it. Like, you have to read the problem very clearly and understand up to where you have to answer. That's what is an examination means. So examination is not writing whatever you know in general. So it is answering or writing what is given. So you have to answer according to the question. So as per this question, you have to formulate and solve. Let us divide the problem into two stages. Stage 1 is formulation. So in which, okay, classical 3 steps will follow, that is declaration of variables, then writing the objective function constraints. Then stage 2 is graphical method. So that is new for you now. Okay, so we have discussed about the procedural steps. Following those 4 steps now, so we can find the solution using the graphical method. Now coming to the stage 1, no, formulation. So as I told, so let x1 comma x2 be the number of laptops and desktops to be manufactured. The objective function so is 700 x1 plus 500 x2, that is Z max, subject to, so the constraint 1 is assembly time. Total assembly time that we have operand is 210, no, 210 hours. Each laptop, no, requires 4 hours of assembly time. Like that, x1 laptops requires 4x1 linear, that's all, no? So that's why it's called linear programming, I said at some point. 4x1 will be the number of hours required for the laptops. 3x2, each desktop requires 3 hours of assembly time. So like that, okay, if you have x2 number of desktops, 3x2 will be the time required for assembly of desktops. 4x1 plus 3x2 will be the total assembly required for both of your products. So is less than or equal to 210. In the same way, you have a constraint on inspection time, that is 2x1 plus 1x2, or simply you can write x2 less than or equal to 90, that is inspection time 90. So 2x1 means each laptop requires 2 hours of inspection time. So like, okay, if x1 units means 2x1 plus each desktop requires 1 hour of testing time, hence it is 1x2, so less than or equal to 90. Then a default constraint known as non-negativity constraint, x1 x2 greater than or equal to 0. You cannot produce negative number of laptops, no, to impose that or to avoid that confusion. So we declare a default constraint known as non-negativity constraint. Now let us see the stage 2. Before that, the set of all points that satisfy all the constraints of the model is a feasible region. That's what, okay, already we have discussed what is the feasible region here in this one. Step 2, common area satisfying all the constraints. Here there are 3 constraints including the non-negativity constraint. Now coming to the graphical solution, what is it as stage 2. So you have to convert the inequality into equation first, then you have to plot it. How to plot the equation? It is simple coordinate geometry. Okay, so what I can say is, okay, you please go back, let us go back to this one. You consider this as an equation, 4x1 plus 3x2 equals to 210 like. So because if it is inequality you cannot plot, so equation you put it, fine. Then if you assume x1 as 0, you will get x2 some value. How much, what is the value of x2? 3x2, it will take 210. x2 is 210 by 3, that is 70. 0, 70 is one pair of coordinate. And okay, on the contrary, you assume x2 as 0, then 4x1 will take the full value, that is 210. So x1 is 210 divided by 4, whatever it is. So like that, you will get the pair of coordinates for this. That's what I mean. Assume x1 as 0, you will get x2, that is one pair. x2 as 0, x1. In the same way, this one also. Okay, if you take 2x1 plus x2 equals to 90, I mean, very first step is always you have to convert the inequality into equation. The constraint you have to consider as an equation. So if you set x1 as 0, x2 is 90, that is 0, 90 is one pair, and x2 if you set it as 0, 2x1 is 90, or x1 is 90 by 2, that is 45. So now coming back to the graphical, this one. So this is the plot. I mean, constraint 1 you have represented, and as it is showing less than or equal symbol, so you put 1 or 2 arrows downward like this. What it indicates means any set of points. Equation means if it is exactly equation means, so no need to show this arrows down. So any set of points on this line from here to here has to satisfy that equation, but here as it is less than or equal, so maybe on this line, I mean set of points on this line or below this will satisfy the constraint. That is the meaning. Or okay, simply you can remember whenever it is less than or equal means, okay, you have to put the arrows down. Now solution space or feasible region considering only this constraint is this much now, this whole triangle. Why? Okay, so this is x1, no? x1 is greater than 0 means this one, x2 is greater than or equal to 0 means here. Okay, considering only this constraint, but you have one more constraint. Let us see that. Now if you incorporate or introduce one more constraint, that is the second constraint, so you will get like this. Again, that is also pointing downwards. So what is that? So 2x1 plus x2 is less than or equal to 90, no? So if you take this one, you will get like this. Again you have to put the arrows downwards like this. Okay, so you have shown downward arrows like this. So x1 is greater than or equal to 0, x2 is greater than or equal to 0. Now if you carefully observe, so this is the common area, that is O, for example, if I call this A, B, C. So this closed boundary is the common area which is satisfying all the constraints. So I mean, you are taking all the constraints into confidence, then you are going to identify the feasible region. Okay, so now definitely this is not the feasible region. You can discard this or you can discard this. So why? Okay, this is not satisfying both the constraints, or even this is also not satisfying the constraints. Hence, this is the most common area shared by all the constraints. So let us name that as O, A, B, C or something like. Now, if you recall the steps or procedure, step 1 we have completed. That's what plotting this lines. Then step 2 is identification of feasible region, that also we discussed. Now let us come to step 3. Step 3 is, so you have O, A, B, C, 4 points, no? So you have the objective function, that is z max equals to something. Find the value of z, no, at each coordinate or at each corner. This is called method of corner points. So O, for example, if you take x1 is 0, x2 is 0, if you substitute x1 and x2 0, z will be 0, of course. Okay, now coming to A, because you have drawn the graph to the actual scale. So actual scale in the sense, okay, you can read directly x1 and x2. Fine, x1 and x2. Substitute the values of x1 and x2 at A. In the same way at B and at C. So wherever you get maximum, because the objective is maximization, it is z max. So that is the answer. I mean, here of course here you will get 0. Here some value will get, here some value, and here some value. Okay, so that is about step 3. Step 3 have completed. Now what is step 4? You can recall. Okay, I am going back to the steps. Okay, you have completed the plotting, you have identified the feasible region, you have obtained the value of the objective function, let us say. Then based on the objective, no, that is maximization in this case, so you have to declare, I mean, wherever the maximum occurs, that is the answer. Corresponding coordinates are x1 and x2. So now, as per this problem, so z max, no, z max is 36,000. So I mean, this is this you are getting at corner point B. Okay, the corresponding coordinates at B are this one and this one. ZA you will get some value. Okay, ZC you will get some value, but of course you have to work out and compare which is maximum. So at B we are going to get the maximum. Please check it. x1 comma x2 equals to 30. So now step 4 is this one. That's all. Maximum Z equals to 36,000. That is the answer, and corresponding coordinates. Okay, x1 and x2. So what is x1 actually? You have declared number of laptops. X2 number of desktops. Your answer is, you are suggesting the company so to manufacture 30 of each. I mean 30 number of laptops and 30 number of desktops to maximize the profit. So in order, I mean, satisfying the constraints, that is very important. Satisfying the constraints means that assembly time and one more is testing time. Now, so only thing is, okay, there are some hints to identify the feasible region. So like satisfying all the constraints, no, it is common area, nothing else. So like if there are two persons, if there is a conflict, no, so we'll come to some agreement, close agreement or amicable solution, what we call. So I mean like satisfying both constraints, both the views. So we'll find a common solution. It is as good as like that. Okay, fine. Now okay, constraint means, for example, one this one will be showing upwards, one will be showing downwards, then the in between space is called solution space. So okay, if I ask like this, for example, above the ground floor and below the second floor means which is the common floor, I mean which is the floor that is satisfying both the constraints. It is like first floor, nothing else. So above the first floor, sorry, above the ground floor, below the second floor, I mean satisfying both the conditions or constraint. What is the answer means? So first floor. Okay, so it is as simple as that. But only thing is, okay, you have to be very careful while plotting. After plotting, no, you have to take care of all the constraints. Then only you have to identify the solution space or solution region. So in fact, there is a theorem. Okay, no need to optimality theorem. When this is a solution space or feasible region, you may get doubt. Okay, so many solutions you will get. Yes, you will get n number of solutions or infinite number of solutions, I can say. So in the solution space, but all the feasible solutions may not be optimum. all the feasible solutions may not be optimum, but what the theorem says is, so just if you find the value of objective function at extreme points means extreme points of the feasible region, it is sufficient. No need to check or test at all the points. Always the optimality lies at the extreme corner points. That is about the optimality theorem. So you will be having n number of points. When it is feasible, no, every solution is a feasible solution, because it is feasible region. Every solution at any point is feasible region. But here, so what it says is, that's what method of corner points I have mentioned somewhere. Method of corner points in the step 3 it seems. Okay, method of corner points, this one. Okay, just you have to find the value of the objective function at corner points or extreme points. Okay, so now so this one O A B C. Okay, even here also we'll be having, so that's what there may be plenty of feasible solutions, but optimal solutions may be one or two. That okay, we'll discuss under special cases. You may have more than one optimal solution also. That's called alternative optimal solution. So now okay, it's like this. For example, if you want to travel from city A to city B, you will be having 10 routes sometimes. All are feasible, but you will not go by all the 10 routes, no? So you will be knowing which is the best route. Fine. So okay, via P, for example, via Q, you have two options only. Let us see. Via P 100 kilometers, via Q 120 kilometers. Fine. Then normally okay, you select via P only. Though it is feasible, the other one also is feasible. So you will think of the optimal, which is the nearest route, or which will take less time, less distance. Like that it is. Fine. Now extreme points and optimal solution. Just to understand, the feasible region and the optimal solution very clearly, still more clearly. So you can see this. Now this is the feasible region, I can say, satisfying all the constraints, assuming that all are showing downwards. These points are there, no? Method of, they are the corner points, or extreme points. So according to that theorem, so though you have n number of points, okay, you can put any number of points, each point will become the feasible point, but each point may not be the optimal. That's why, so just you have to check at this point, at this point, they are the boundary points. Fine. Now let us see one more problem. Solve the following LPP by graphical method. Minimize Z equals to subject to some constraints. Now let us see the change between this and previous problem. Previous problem was maximization, that is one change you can see. And the previous problem, constraints were one side, less than or equal, like that, except the default constraint. Default constraint always will be greater than or equal. And one more thing is the objective is minimization. So nothing to do with the objective function at this stage. For plotting the graph, objective function will not come into the picture, only the constraints. So now procedure is same, whether it is minimization problem or maximization problem, procedure is same. Let us follow the typical procedure, that is 4 steps. So here already it is formulated and given for you. That is only stage 2 you have to take care of it. Stage 2 in the sense the graphical solution. So no need to declare the variables, no need to write the objective function, everything is given to you, just you have to solve it. Fine. Now first step, okay, what is the first step? So you have to convert the inequalities into equations and you have to plot them. For example, this one, 4 inequalities are there, 3 including the non-negativity 4, of course that you are not going to plot. So whether it is less than or equal or greater than or equal, whatever it is, so convert the inequalities into equations. That's what the first step says. So then you have to obtain the values of x1 and x2. x1 0, you take x2, x2 0, x1. So in the same way for other constraints. Now let us see. First constraint I have plotted like this. Okay, as of now this is the feasible region if only one constraint was there. Okay, so it's showing downwards because, so less than or equal type it is. Fine. One more constraint. Now you can see the change. So it is showing upwards. Any set of points which will lie on this line or above only will satisfy that constraints. Something should be greater than or equal, no? Okay, now, so if you identify previous one and this one, here This was the feasible region. After incorporating or introducing this one, no, so this became the common area. So this is not common area now. Now one more constraint to incorporate. Again, that is showing upward, no. Okay, now if you observe, so which is the common area? This one. Definitely this one. You can shade it or hatch it. So this one is not common area, this one is not common area, I mean it's not satisfying all the constraints, this one also. So only the area which is satisfied, I mean this is showing downwards, this is showing upwards, taking all the constraints into consideration. So you have to identify the feasible region. Of course x1 comma x2 greater than or equal to 0, that will be there. So it indicates first quadrant, no, I mean non-negativity condition. Now so don't think that always the feasible region should start from origin, need not be, okay. So it may start somewhere also. In this case, okay, what are the corner points? Let us see, A, B, C and D like. Now two steps you have completed. What are the two steps? You have converted the inequalities into equations. So you have plotted the graph. Then after plotting the graph, you have identified the feasible region. Then third step is, as per that procedure or steps given, you have to obtain the value of Z at this point. At this point, of course, we'll name that as A, B, C, D. Fine. X1, X2 greater than A, B, C, D. So Z value you have to obtain at each coordinate or each extreme, A, B, C, D. And as the objective is minimum, wherever you get minimum, okay, that is the answer, and corresponding coordinates are X1 and X2. Directly you can read from the graph. That is step 4. At A you have to take the value of X1 and X2. For example, at A, no, X1 is 0. So, X1 is having some value, X2 is 0. At B also, X1 is 40, X2 is 0. At C, you have to read, this is the X1 and this is the X2. At D also, so this is X1, this is X2. Is graphical method, no need to solve any equations. Of course, you can solve a simultaneous equations and you can find the coordinates of C and D. That becomes the mathematical or analytical approach, which you are not supposed to do, because you are giving the graphical solution. Directly you have to read from the graph only. Now, so if you see, these are the constraints, fine. Okay, of course you will get the value of Z somewhere, wherever you got minimum, no, wherever you get minimum, so that is the answer, fine. Now let us take a few more problems of the same concept. Maximize Z subject to some requirements like, let us see what is the change. Okay, so profit in the sense you have to maximize, okay, these are the requirements, the constraints, I mean production time, total production, okay, all this 1, 2, 3, there are 4 constraints and this is a default constraint. Now graphical analysis, the feasible region. As of now, no, so the feasible region is this one, I mean only if this is the constraint. Okay, infeasible, feasible. Okay, if you have this, okay, the triangle portion, no, will be the feasible region. Okay, then if you incorporate one more constraint, this will be eliminated. Okay, so this will show you how to identify the feasible region. Fine, this becomes feasible now. Okay, now if you incorporate one more, no, this will be eliminated. Okay, so whether the constraint is showing upwards or downwards, that you have to see, and you have to go on seeing the changes. Fine. Now this is the feasible region. Of course, same old 4 steps. What are the 4 steps? Okay, you have plotted the graph, identified the feasible region, then you have to obtain, I mean you have to identify this as, okay, something O, A, B, C and D. At each corner you have to find the value of Z. Now there are 3 different types of feasible points we can say here. One is this is interior points. There will be plenty of interior points, but nothing to worry about all those points. Okay, only the boundary points, no, that's what we're discussing now. Step 3, boundary points means O, A, B, C, D, and these are the exterior points. They will not come into the picture, so because it is infeasible, not in the consideration at all. So only this one, boundary points, okay, you have to take. Fine. Now let us see one more problem of the same type. Okay, minimize. Okay, so that is equal to 2500 x1 plus 3000 x2 subject to some constraints like, See, like this, okay, we'll get, because it is given upwards. Why you have shown the arrows upwards means, so it is the constraint type is like this, greater than or equal. This is also like that. Okay, fine. Now why, okay, we're discussing this problem means, so don't think that always feasible region means that okay, it is bounded or closed or something like. So depending on the constraints, it may be like this also. So what I mean to say is, here there are 2 points A and B. This is the feasible region. Of course, the objective is minimum, no? That's why you can find the value of Z. Okay, first 3 steps you have completed. You have plotted the graph, you have identified the feasible region. Now in step 3, no, Z value at A, Z value at B you are going to find. Step 4, of course, declaration of Z minimum, whether you are getting at here or here. Okay, so that's what. Okay, if it is, as it is minimization, okay, you have the solution for this. If it is maximization, it will become a special case. It will become unbounded, because if you keep on increasing the value of x1 and x2, Z max also will increase. That will become under that will be a special case. So what I mean to say is, so as okay, if you see the objective function, it is minimization. There is possibility for minimization here. It is the feasible region, you can say. So now you have to find out, okay, only 2 crossing points will come. Don't think that okay, you have to get plenty of crossing points every time. So always you have to start the feasible region with origin. No, not required. So it depends upon the constraints. Now, okay, you may get what is this point or this point, because it's like a rectangle shape. No, this corner, no. So only the crossing points, I mean, crossing points means, see, only at A and B. So you have the crossing point. Okay, that is called boundary point. Boundary point. This is the boundary point. So this is not a crossing point. Okay, this is also not a crossing point. Okay, fine. Now total cost at corner A is something like 1,60,000. At B is 1,65,000. Okay, because at A, no, x1 is this much, x2 is this much. At B, x1 is this much, x2 is this much. Now as the objective is minimization, so lowest total cost is at point corner A. Corner A means this one. Okay, fine. Then your answer is x1 is this much and x2 is this much. Fine. Now special cases in graphical solution or graphical method. So far we have discussed a unique solution. Sometimes okay, it may have variations. Let us discuss what are the variations. So infeasibility occurs when a model has no feasible point. What happens means, don't think that all the LPPs will have the solution. So one constraint will be showing downwards, one constraint will be showing upwards, and you will not be in a position to identify the common area satisfying both the constraints. In such cases, it is called infeasibility or no solution case. We'll take a problem on each case. Okay, so occurs when a model has no feasible point. No, basically there will be no feasible solution at all. So that is called infeasibility. Unbounded solution. So occurs when the objective can become infinitely large or maximum, or infinitely small, or whatever it is. See, let us take like this. Objective function is maximization, that is Z max. All the constraints are showing upwards, greater than or equal to 0, greater than or equal to 0, or something like. Then there is no point of maximizing it. If you keep on increasing the values of x1 and x2, the value of z also will increase. So that case is called unbounded. I mean, there is no boundary. If there is much demand for a product, if you keep on increasing the production of the decision variables like products, what I can say, the profit also will increase. It's unbounded. Okay, there is no boundary for solution or profit. Okay, so that we'll see. Okay, with the numerical we'll see. Then alternate solution, alternate optimal solution, what I mean. So minimum or maximum may occur in 2 places, like, I mean, method of corner points, if you recall. So z min or z max. So at 2 corner points, assume that a feasible region has 4 corners. At 2 corners, for example, objective is minimization. At ZA you got 20,000, ZB also 20,000, ZC 30,000. So the minimum is 20,000 and it is repeated. In such cases, so you have to see, I mean, the conclusion is the problem is having alternate solution. So answer is same, but you can vary the products, like, I mean, number of products x1 and x2, you can have the different values, but the value of the objective function will be same, minimum or maximum. That is alternate solution occurs when more than one point optimizes the objective point. It is like this. Okay, again I'll take the traveling example from A to B. So assume that, okay, you have two options to reach B from A, via P and via Q. So if you go via P also exactly 100 kilometers, via Q also 100 kilometers. No change in road condition also, let us see, exactly 2 hours you require either way. So then what you can say, so what you will choose? Either way, I mean alternate optimal solution. Whereas assume that, okay, A to B, one is 100 and one more is 120, one takes 2 hours and one more 2.5 hours. Both are feasible, but only you have one optimal solution. Whereas if you have same answer, I mean 2 hours exactly as well as 100 kilometers, so then you can say that the problem is having alternate solution. Here mathematically we can say that all feasible solutions may not be optimal. Please listen carefully. All feasible solutions may not be optimal, but an optimal solution necessarily should be feasible. So you will be having plenty of what feasible solutions for a problem, let us say, but all feasible solutions may not be optimal, but a feasible solution necessarily should be an optimal, an optimal solution necessarily should be feasible basically. Okay, so it is like alternate solution is like this. Assume that in module 1, okay, in a particular examination you got 2 questions, no, or I will be having internal choice, fine. So question number 1 20 marks, question number 2 20 marks. You are very confident that, okay, you will get 20 marks either attempt question number 1 or question number 2. You are equally confident. So then, so either one you can take, no. So it's like you have the choice. Okay, it's like tie. What I can say, tie. There is tie. Either you can answer question number 1 or question number 2, as you are expecting or hoping that you will get the same result. Okay, so we'll discuss more with some numerical or example. Then one more thing is redundancy. A redundant constraint is a constraint that does not affect the feasible region in any way. Sometimes there will be some dummy constraints, so that is called redundancy. It will not influence the feasible region or solution whether you have it or not. So the constraint will not change the answer or feasible region. So that is called a redundant constraint. First one, let us see the infeasible case, that is no solution I was telling. Now if you carefully observe this, so there are 3 constraints. One constraint is showing upwards, one more downwards like this, third one also like this. Now satisfying 2 and 3 have the common area or feasible area, but this is somewhere going upwards. Now if you analyze, there is no area, no common feasible region satisfying all the 3 constraints. Hence the conclusion is infeasible solution or no solution, like, fine. I mean no solution in the sense, so that is also a solution. Okay, so or you have to change the constraints. You have to change the constraint. Okay, if you change the constraints, there may be solution. That is not in our scope. I mean, based on the given problem, there is no, or based on the given constraints, there is no solution or infeasibilities, like. Okay, now let us see with the numerical. So a condition that arises when an LP problem has no solution that satisfies all of its constraints. Now see, these 2 constraints are showing downwards. Okay, this is the region satisfying first 2 constraints, whereas region satisfying third constraint. He is playing here, these 2 people are playing here, like. So there is no commonality or understanding or this one common area. So hence, so it is infeasible. I mean, satisfying all the 3 conditions or constraints, you are not in a position to identify the common. Can you say this is the common area? Never. Not this one, not this one, not this one. Okay, if you can you take this one, then you are considering only constraint 3, or can you take this, then you are ignoring this constraint. Hence, so this problem has no solution or is having infeasible solution, like, fine. Now unbounded. Okay, if you take this example as I told, Z max, okay, is equals to this one. Objective is maximization, all the constraints also are showing upwards, you can see. So just by observing itself we can say it's unbounded. So we can sense it or we can guess it like, okay. So even without solving. Why? So objective is maximization and all the constraints are showing greater than or equal. Then how will get the boundary? You will never get the boundary. Okay, if you keep on increasing the values of x1 and x2, z also will keep on increasing. Only at infinity you will get the maximum. Hence, okay, this is unbounded case, we can say like this. So if you keep on increasing the value of what? x1 and x2, so the feasible region is unbounded. Feasible region itself is unbounded. So the objective function, which the value of z no is maximum at only infinity. This is unbounded case. Then alternative optimal solution. That's what, okay, I have told, having the same answer, maybe minimum or a maximum, same answer in the sense, okay, at two corner points. So this also you can guess in advance what I can say. So whenever slope of the objective function is parallel to one of the constraints, mathematically slope of this and slope of this is same, you can see 3 2, slope is 2 by 3 or so, 4 by 6, so same, slope is same like. So I mean slope of this is parallel, no? Parallel means, for example, proportionally if you take, this is also 3x1 plus 2x2 less than or equal to something, it will become fine. So in such cases, so you can feel that or you can guess in advance that, oh, the problem is having alternate solution. Otherwise, okay, no need to guess like that, just you can solve and finally you will come to know so whether you have the alternate solution or not. But this is for competitive exams and all, no? Just by seeing itself, okay, you should be smart enough or should be quick enough to guess. Fine. Now, if the objective function is parallel to one of the constraints, then multiple solutions exists. Okay, like this. So, for example, if you solve this one, z max, no? So 3 points have. Z max may be same at any of the 2 points. So please verify that. Maybe here or here and here. Here and here, the combinations. Maybe here and here or here and here. Z max will be same, okay, at 2 points. Then, okay, Z max will be same. There is no change in Z max. That's what, okay, you can have the choice of having x1 this much, x2 this much, or x1 this much, or x2 this much, if the value is repeated here and here. Okay, I mean, you will be having the choice of having the variables. Okay, now the last one is the redundancy. So redundancy means a constraint, is a dummy constraint which will not influence your solution space or answer, I said. Okay, now if you take this plot, no, okay, it is plotted as per the given problem. Okay, is a redundant constraint, I can say. This is the feasible region. Of course, this also, okay, this is not pointing like this. If it is pointing like this, it will become the first case, that is infeasible case it will become. But it is showing downwards only. Please observe the change. See, in the first case that we discussed, this was showing this way. Okay, not this way. So here in the redundancy concept that we are discussing, so here, I mean, whether you consider this or not. Okay, if you consider this, this will be the feasible region, less than or equal, no? This is less than or equal. So even if you discard this, so the solution space is same, or even if you have this, the solution space is same. I mean, no need to give importance for this constraint. Okay, so you can just ignore it. That is the meaning of redundancy. So the concept of redundancy is, a redundant constraint is a constraint that does not affect the feasible region in any way. Friends, that's all about graphical solution and its special cases. I hope certainly you will meet the learning objectives by this. Learning objectives or outcomes, as we discussed, is to understand the graphical method, to understand the special cases, and to know the limitations. Limitations of the graphical method is, the main limitation of the graphical method is, if you have more than 2 variables, it's not viable or feasible to use. You have to go for analytical methods such as simplex method and so on. Fine. So to summarize in a nutshell, you have to understand the steps, no? 4 steps. Step 1 is converting the inequalities into equations and plotting in the graph sheet to the actual scale, of course, or to the proportional scale as required. Then second one is identifying the feasible region, the region which satisfies all the constraints. Third step is, so no need to find the value of z at all the points. So there is a theorem I said. So according to that, extreme points of that boundary, no, you have to take, and you have to obtain the value of z at each extreme points. Based on the objective, you have to declare the optimality. I mean, if it is minimum, wherever you get minimum, no, so that is the answer. Corresponding coordinates are x1 and x2. If it is maximum, it is accordingly. I mean, so wherever you get maximum, so you have to declare that as optimal solution, and the corresponding x1 and x2 directly you can read from the graph. Then we discussed about special cases. Special cases means infeasibility or no solution, unbounded, alternate optimal solution. Alternate optimal solution means same problem is having like two solutions. Okay, sometimes it's also called as multiple solution. Like multiple solution means sometimes three solutions also you may get, but in general, okay, alternative optimal solution we use it. And then redundancy. So redundancy is a constraint which will not influence your feasible region. Friends, I take this opportunity to express my sincere thanks for your kind attention. With this, we have completed session 3, that is linear programming graphical solution. We'll meet in the next session. Till then, take care and have a nice time. Thank you.